Welcome to our new lecture where we are going to continue our discussion on soil consolidation. To give a quick recap of what we studied last week, we tried to explain soil consolidation by giving an analogy of a spring cylinder assembly as shown in these figures. We tried explaining that how when the load applied on a saturated fine-grained soil, immediately upon the application of the load, the pore water cannot escape through the little voids that the fine-grained soils have. So because of this, the pore water pressure builds up within the soil. However, after some time, this pore water gradually starts releasing, and once it starts releasing, the pore water pressure keeps on decreasing, and the load, which was initially being carried all by water, now transfers slightly to the spring, that is the soil solids. And then after when considerable amount of time has been elapsed, all the excess pore water pressure has been dissipated, and all the load which was initially being carried by water and partially by soil solids is now transferred to the soil solids only. Knowing this, we talked about the three major kind of stresses that are involved in this process. One is the total stress represented by sigma, which is represented by the total load which is applied on our assembly. Pore water pressure, which represents the water pressure within the pores of the soil. And finally, the effective stress, which represents the particle-to-particle contact pressure. And their expression is simply represented by this equation. So what inferences can we derive from the spring cylinder model, and how can we use the knowledge obtained by the spring cylinder assembly for the practical soil mechanics? Now, whenever we talk about soil consolidation, we are mainly interested in determining two things. First one being the magnitude of consolidation settlement. As we talked, that when we apply some load on the soil, for example, when we construct some house on a soil which is subjected to consolidation settlement, our first concern is that what would be the total magnitude of consolidation settlement? What will be the total settlement because of consolidation that will occur over there? And since consolidation is a time-dependent phenomenon, because of the time-dependent nature of consolidation settlement, we are also interested in determining the rate of consolidation settlement. That is, at what rate this consolidation would occur. What would be the speed of this consolidation? So these are the two things which are important for us when we talk about consolidation. So in all the numericals that we'll be doing, we'll either be calculating the magnitude of consolidation settlement or the rate of consolidation settlement. So these are the two things that are important for us. Now, thinking about the magnitude of consolidation settlement, just think for a moment that if we consider the spring cylinder assembly, what are the factors upon which the magnitude of consolidation settlement would depend upon? So we can think either based upon the spring cylinder assembly, or in case of the real soil, what are the main factors upon which the total magnitude of consolidation settlement depends upon? So the total magnitude of consolidation settlement basically depends upon the compressibility of the soil. That is, if we talk in terms of spring cylinder assembly, that what is the spring stiffness of the spring? So stiffer the spring, lesser will be the magnitude of settlement, and softer the spring, more will be settlement. In the same way, the particle to particle metrics, the stiffness of the soil, higher the stiffness of the soil, lesser will be the magnitude of consolidation settlement, and vice versa. In the same way, let's think for a moment that what can be the possible factors upon which the rate of consolidation settlement depend upon. The rate of consolidation settlement depends upon the permeability of soil, and also the compressibility of soil. Now see, we are talking about the speed at which the soil can settle, that is the rate of consolidation settlement. So obviously, the quickly the water can move out of the soil matrix, faster will be the faster will be the rate of consolidation, faster will be the rate of settling of soil. So and so the speed of water ejection from the soil is what we call as permeability, and also it depends upon the compressibility of soil. Now, talking about the magnitude of consolidation settlement, when we talk about the magnitude of consolidation settlement, this is generally expressed in terms of an index which is known as compression index, represented by C subscript C. So remember, talking about magnitude of settlement, if we are to determine the magnitude of settlement, that is generally expressed in terms of compression index. So whenever we have to determine the magnitude of settlement, we will determine magnitude of settlement by using compression index of soil. In the same way, the rate of consolidation settlement is expressed in terms of a coefficient, which is known as coefficient of consolidation, represented by CV. So whenever we are required to determine the rate of consolidation settlement, we make use of CV to determine the rate of consolidation settlement. Now, if we know the magnitude of consolidation and if we know the rate of consolidation settlement, knowing these two things, don't you think we can determine the time required for consolidation as well? If we know the magnitude of settlement and if we know the rate of consolidation settlement, then obviously simply by multiplying both, we can easily determine the time required for consolidation settlement. However, there's an alternate way of determining the time required of consolidation settlement, and that is given by this expression. Now, this is the expression which explains the time required for consolidation settlement. Now, what this expression is, we can see this expression, the different components of this expression, where this T is the time required for any degree of consolidation. CV is the coefficient of consolidation, as we have explained on the previous slide, and H represents length of the drainage path. Now, this length of the drainage path is generally either taken as T, or in case of one-way drainage, or it is taken as T by 2, that is thickness of the consolidating layer by 2 in case of two-way drainage. Now, what is one-way drainage and what is two-way drainage? That is something that we'll study in the coming slides. So I'll just move forward, skip this and move forward for the time being. This capital T, which is used in this equation, it is a constant which is known as time factor. Now, what is time factor? Time factor can be determined by using this equation. And in this equation, it is simply pi by 4, u by 100 square. Now, what is u? U is a parameter which is known as degree of consolidation. Now, U is known as degree of consolidation. So if the degree of consolidation is less than 60%, then we can determine time factor by using this equation. However, if the degree of consolidation is greater than 60%, we have to use this equation for the determination of time factor. So you see, what we are doing is, in this equation, we are replacing the value of time factor directly from here. H, which is the length of the drainage path, that is something we can determine from the geometry of the problem. And CV, which is the coefficient of consolidation, is the soil property. So by knowing all these things, we can easily determine the time required for consolidation. So this is how we can determine the time required for consolidation. But when we talk about time factor, this capital T, there are two values of time factor which are very commonly used in soil mechanics. So I would suggest you to remember these two values. So time factor for 50% consolidation, time factor for 50% degree of consolidation, which is represented as T subscript 50, is 0.197. So you should remember that T50 is 0.197. In the same way, the time factor for 90% consolidation is 0.848. So these are the two values which you should remember because they'll be very frequently used in soil mechanics. So knowing this thing, we can explore a little bit more about the time of consolidation, or this time required for consolidation, which is also called as consolidation time. So this is the expression we have studied on the previous slide, and this CV can also be determined by using this expression. Now, in this expression, this K is the coefficient of permeability, and MV is coefficient of compressibility, and gamma W represents the unit weight of water. So we'll talk more about this equation later on. So what we can do is we can replace the value of CV into this equation, and we'll come up with one comprehensive equation for consolidation time. So by using this equation, we can determine the consolidation time as time factor times length of the drainage path squared times unit weight of water times compressibility index divided by the coefficient of permeability of soil. Now, a very interesting thing to observe from this equation is that we want to determine the time required for any degree of consolidation, the consolidation time. And this consolidation time is independent of the magnitude of stress that is applied on the soil. You see, there is no variable representing the stress in this equation. It means that the consolidation time is independent of the applied stress. To understand it a bit better, let's look at this figure. It means that if we have a clay soil which is fully saturated and we place two loads, load A and load B on the soil, the time required for 50% consolidation in both cases would be the same. In the same way, time required for 90% consolidation, both in case of load A as well as in case of load B, would be the same. This shows that the time of consolidation is independent of the applied stress. However, you can note this thing that because this load A is smaller and load B is bigger, so it is possible that the overall magnitude of settlement for load A is smaller. For example, it is possible that the total magnitude of consolidation settlement because of load A is 100 millimeters, and the total magnitude of consolidation settlement for B is 200 millimeters. But that what we mean by these equations is that the time required for 50% consolidation to complete, both in case of load A and load B, would be the same. What it means is, remember, 100 mm consolidation and 200 millimeters consolidation. So time required for 50% consolidation, that is 50 millimeters in case of load A, and 100 millimeters in case of load B would be the same. So the time required to achieve 50% consolidation settlement, which is like 50% mm and 100 mm, would be the same in both cases. Same would be the case when we talk about 90% consolidation or any degree of consolidation. Now, moving to the real case scenario and talking about the consolidation settlement in the field. Now, this figure represents a real field scenario. It is very possible that you have a project site where we have sand overlaying a clay layer and there is another sand layer underneath. Now, since we have groundwater table here, it means this clay layer would be fully saturated. Now, if we construct a building here, means if we apply an external load, delta sigma, what will happen to these soil layers? Now, because of the application of the external load, the soils would get compressed. When the sand layer would get compressed, what would happen to the sand layer because of compression? When the sand layer would get compressed, because of the high permeability of the sand layer, there would be very quick drainage and there will be immediate settlement in the sand layer. So, whereas what will happen in the clay layer, because of the application of the applied stress, this clay layer would try to get compressed. However, however, the water which is in the pores of this clay layer, it would be difficult for the water to leave the clay layer because of very low permeability. And because of very low permeability, it would be subject, the settlement would not occur immediately, rather it will take considerable amount of time. And whenever there is considerable amount of time which is involved in settlement to occur, this is what we call as consolidation settlement, which is a kind of time dependent settlement. So this is the difference between the two kinds of settlements that occur in case of granular material and in case of fine grained material. Now, there is another concept that you should know before we move ahead, and that is of one-dimensional consolidation. Now, what is one-dimensional consolidation? One-dimensional consolidation is a simplification of the real field scenario. In the real field, the settlements are taking place in 3 dimensions. However, what we do is we simplify the overall scenario. We simplify the scenario and we assume that the settlements are only taking place in one direction. We assume that the drainage can only occur in the vertical direction, that is, the water can leave this clay layer either from the top or from the bottom. So we assume that the drainage can occur only in one direction, and if the drainage can occur only in one direction, it means the settlements can also occur only in one direction, and there are zero lateral deflections in the soil. So this assumption is what is called as one-dimensional consolidation. Now, this is a reasonable simplification which is done for solving consolidation problems. Now, if you know about the one-dimensional consolidation, there is a complete theory of one-dimensional consolidation theory, which was presented by Carl Terzaghi in 1936. And uh, even in modern times, for all the practical purposes, we make use of one-dimensional consolidation theory to determine the consolidation settlement in soil. These are some of the basic assumptions of one-dimensional consolidation theory. The first one is that the soil has to be homogeneous. The soil has to be fully saturated. As you would remember, we already said this, that consolidation can only occur in fine-grained soils, and those soils have to be fully saturated. The third is that the coefficient of consolidation, I hope you remember this coefficient, that this is something that we use for determining the rate of consolidation. It remains constant throughout the soil mass and also remains constant with time. The coefficient of permeability is constant throughout the soil layer. The Darcy's law, which we have already studied in our previous chapter of permeability, that is V equals Ki, is applicable. And we also assume that consolidation is a one-dimensional problem. That is, the water flows only in one direction and the settlement also occurs in one direction, that is the vertical direction only. And finally, we assume that the soil particles are assumed to be incompressible, which means that we assume that all the settlements are occurring because of the expulsion of water from the soil layer. So how do we perform how do we perform the consolidation test in the laboratory? Now we have seen this figure in the field. We have said that when we apply some load on top of the ground, because of the application of this load, the soils get compressed. So because there is immediate settlement occurring in the sand layer, so we are ignoring the sand layer right now, and I'm only going to discuss the clay layer, because clay layer is the one in which consolidation settlement would occur. So when we apply load on the ground, there is compression in the clay layer. So when we want to perform this consolidation experiment in the laboratory, what we do is we take a soil sample from the clay layer. What we do is we perform a borehole, and from that borehole, we take a relatively undisturbed sample, a sample which is representative of its properties within the ground. We take that sample and we we call it as an undisturbed sample. As I said, what is an undisturbed sample? An undisturbed sample is the one whose properties, we take the sample out very carefully from the borehole, and we take it in such a way that the properties of the sample are exactly the same or nearly the same as it was in the ground. So we take an undisturbed soil sample, we fix this soil sample inside a metal ring. So we just take a metal ring, and inside that metal ring, we fix this. So this is the top view of the metal ring. And then what we do is we fix this metal ring inside a water-filled container. So what we do is, this is a container, which this is a cross-sectional view of a container which is filled with water, and these lines here and here, these are the sides or the edges of the metal ring. So this is a circular metal ring. If I cut a cross section and view from the side, I will see it will appear like this. So this is the boundary of the metal ring, and inside the metal ring it is filled with soil, like it is filled with soil over here. So what we do is, we put this metal ring inside a chamber which is filled with water. Below this metal ring, below the soil surface, and on top of the soil surface, we put some porous stones. Now these are simply some stones, something like brick material, but this is a disc of brick, you can say. So it is having very high permeability. So we put this porous stone at the top, and put the same porous stone at the bottom. Now, and then we apply a plate at the top. So this green one is a large dia plate that we apply on the top. And then finally, we apply pressure. We apply a load at the top of this one. The important thing to notice here is that if you look at this assembly closely and compare it with the field conditions, you'll see that what we have done here is that we have replicated the whole field condition on a small scale in the laboratory. What I mean is, now imagine that this soil sample which is here is the same soil which was placed here. Now, the soil, when it was in the field, it was under water. So the soil here is again underwater. So it means that the soil here would again be fully saturated. This clay layer had a pervious layer at the top and a pervious layer at the bottom. By placing a porous stone at the top and a porous stone at the bottom, we have reproduced the same condition, that on top of the clay layer and at the bottom of the clay layer, there is a pervious layer. Then we applied load on the top. And this is what we have done. We have applied load on the top by using this assembly. And finally, since our soil sample was undisturbed, because our soil sample was undisturbed, it means whatever was the density of the sample and whatever was the natural moisture content of the sample, same natural moisture content and same density of the sample is what we have achieved over here. So in a nutshell, what we can say is that we have reproduced the whole field conditions on a very small scale in the laboratory. And this is what we actually want to do with any experiment in the laboratory, that we want to scale down the whole field conditions onto a smaller scale so that we can control the conditions better and we can observe the related phenomena. So this chamber that we use is known as consolidometer or oidometer. So this complete assembly is known as consolidometer or oidometer or a consolidation apparatus. Then what we do, we put the load on top, and once we apply the load, this load, we monitor the deformation in the soil, and because this consolidation is a time-dependent phenomenon. It is not going to occur immediately. What we do is we take the readings of this dial gauge at certain time intervals as well. So for the performance of the test, what we do is we are trying to replicate the field conditions. Suppose this total stress that we applied in the field was 100 kilopascals. So our ultimate goal is to apply 100 kilopascals here as well. But what we do is we apply this 100 kilopascals in small loading increments. For example, first of all, we apply 20 kilopascals. We applied the load of 20 kilopascals and we start the stopwatch. We start the stopwatch and we note down the dial gauge reading. We applied the load, we took the dial gauge reading at 1 minute, at 2 minutes, at 3 minutes, at 5, 10, 20 minutes, at 1 hour, and so on. So what we do is we applied the first loading increment, which was 20 kilopascals. And because consolidation is a time-dependent phenomenon, we took its settlement readings at regular time intervals. So we keep this load applied and we keep taking these readings for at least 24 hours. Then we apply the second loading increment. So first loading increment was 20 kilopascals. Let's suppose we apply the second loading increment as 40 kilopascals. So as soon as we increase the load up to 40 kilopascals, we again start the stopwatch and start noting the dial gauge readings at 1, 2, 3, 5, 30 minutes and 1 hour, etc. And we keep noting these readings until the dial readings have stopped or 24 hours have been elapsed. So it means each loading increment that we have applied is kept for 24 hours, is maintained for 24 hours. In this way, first we applied 20 kilopascals, secondly we applied 40 kilopascals. In the same way, we have increased the load into increments until we reach our required maximum value of 100 kilopascals. Finally, we apply 100 kilopascals here and again take down different readings at 1 minute, 2 minutes, 5 minutes, and so on. So this is how we perform the consolidation test. Important thing to note is that there are just 3 observations that we are recording during the whole test. What are those 3 observations? The first observation is the applied load. Second observation is the time. And the third observation is the dial gauge reading. So these are the only 3 observations that we are recording. Load, dial gauge reading, and the time interval at which those dial gauge readings are recorded. So let's move ahead. Now, this consolidation test was devised by Carl Terzaghi, and the apparatus is called as the consolidometer and oedometer. The soil specimen is placed inside a metal ring, 2 porous stones, one placed at the top and one placed at the bottom. Now, this is a summary of the same thing that we have discussed previously. Some further details of this experimental apparatus are given here. The diameter of the specimen or the diameter of the ring is generally 2 to 3 inches. The diameter to height ratio has to be between 2.5 to 5. It means the diameter should be 2.5 to 5 times greater than the height of the specimen. You can see the diameter is much larger compared to height of the specimen. So the dia has to be 2.5 to 5 times the height. The specimen must be kept submerged in water. The load is applied through a lever arm. Now, this is something that you'll learn more about in your lab, how the load is applied. And then each load is applied for 24 hours or till the deformation becomes negligible. Each loading increment is generally double the previous loading increment. It means if first you applied 10, if first you applied 10 kilograms of load, the second would be 20 kilograms, third would be 40, 80, 160 kilograms, and so on. Once you have applied all the loads, then finally you also apply unloading. So first we apply all the loading increments, and once all the loading is done, we start unloading the assembly, and the unloading is again done in certain steps. So as I said, that basically there are just three different readings that are taken in this experiment. One is the load, second is the dial gauge readings, and third is the time. So by using these three readings that we take, there are certain graphs that are then made. So our next discussion would be regarding all those graphs that are made. But in this lecture, I'm only going to give you a brief overview of one of those graphs, which is called the deformation time plot. So you see, what we do is the two readings that we take during the experiment are deformation and the time. So if we plot the time on x-axis on a log scale and we plot the deformation on y-axis, we get this kind of a graph for the consolidation test. Now this graph can generally be divided into three zones, as you can see here. This stage one is something we call as initial compression. So when you put the load on the sample, there is some initial compression in the sample. So this is what we call as preloading. Then stage two is called as primary consolidation. This is this straight line part, almost a straight line part. This is something we call as primary consolidation. Now what happens in this part is that this deformation which is occurring, in this stage two is mainly because of the expulsion of water from the soil sample. And finally, stage three is what we call as secondary consolidation. Now, the secondary consolidation is something like creep loading that we have. So because of the sustained loading, this is some plastic readjustment into the particle takes place, and that is we call as secondary consolidation. So this has been the brief overview of the laboratory consolidation test. Next time, in our online discussion session, we'll discuss more about it. And in the next class, we'll see what more graphs can be made and how this